So in here, you want to first start off with the integral notation of this guy. So we're going to change the x to 1. So I'm just going to repeat what I did a second ago. 0 to 1 of 2t plus 1. And then I want you to physically graph what it does mean graphically. So the line that you see there is actually 2t plus 1. So for each of them, I gave you the line x equal to 1, so the integral would say it's the net signed area. In this case, all the areas are positive, so the total area and the net signed area actually end up being the same value. But I am going to keep saying net signed area every time I talk about integral. So there is each of my areas. So what you'll notice is that the area physically depends upon where I place my x. So because my x's are different, the areas are physically different. So therefore, the integral f depends on the variable x. So the x changes, the areas change. Simple concept. So we're going to go into a little bit more depth with that. So I'm giving you the exact same integral from the beginning, and what I did was I put a derivative in front of it. So now you're taking the derivative of an integral, which in your head right now you should be thinking to yourself, well, when you do an integral, you go back, but then I want to take a derivative, so I want you to kind of mentally play with the fact that you're doing a derivative and an integral mentally. You're not going to say it out loud, because now we're going to physically do it. I'm going to make you do the integral portion first, so right now, by hand, I want you to integrate that. So antiderivative, f of b minus f of a. So find the antiderivative, do your f of b minus f of a. Do that part first. Alright, so your antiderivative was t squared plus t. Then I asked you to find the f of b minus f of a. So f of b would be f of x, and that'd be x squared plus x. F of 0 would just be 0. So I'm going to take the problem, that's just the inside box, the red box. So I'm going to rewrite everything as the derivative of f of b minus f of a. So f of b would be x squared plus x. F of a would be 0. And then I want to take the derivative of it. So the derivative of that would be 2x plus 1, which looks very similar to what we had before. Similar, not exactly the same. So now I want you to do the same thing for the next two. So you do your second one, and you pretty much only need to find f of 3, which gives you 3 squared, 9 plus 3 is 12. So then when you take the derivative of that, so you would be finding the derivative of f of x, which we found already. So f of b minus f of a. But when you take the derivative, you end up with this again. Therefore, without me doing the last one, what do you end up with? 2x plus 1. So if you look at all three, so let's look at commonalities. Every single one of them says to take the derivative of an integral. That's the one thing. Every single one of them has an x on top. Every single one of them has a constant as the lower limit. But the constants were all different. So what do you notice about the constant? It doesn't matter at all. You get the same answer when you're all done, whether the constant was 0, 3, -2, pi, e, sine of pi, sine of e. All of those will give you the same exact answer. So this is, in short, what the fundamental theorem of calculus 1 does for you. It kind of starts to explain the fact that the derivative, in a sense, undoes the integral. So there's your fundamental theorem of calculus. It says that when you take a function that's continuous on an open interval I, so some interval, containing an a, that constant, for every x in the interval, you can do this to it. So it essentially says you can take the derivative of an integral from a constant to x of a function, and it'll just be f of x again. Key is there must be a derivative of an integral. If I erase the derivative, it's no longer the fundamental theorem, and it doesn't work. Okay? So only works when my derivative happens of an integral. So this can be any constant. Doesn't matter what the constant, always gets the same answer. And we just kind of showed that through doing a few of them. You'll notice that that constant at the bottom always gives a constant, and then you take the derivative of that constant. That's the real reason of why it wouldn't matter what the number was. Okay? So that's going to be extremely important. So we did 2 days of FTC2. There's 5 days of FTC1. That's because this is really, really important. Once you learn this, you can do a whole bunch of free response questions, and that's the reason why I make that 5 days long, because you're just going to practice a lot of free response. Okay? So, I would like for you to, very quickly, without showing too much work, try those. And then you'll start to notice things. Alright, so like I said, I wanted it to be done with the FTC1. So you're not finding an antiderivative, you're not doing f of b minus f of a, you're taking the physical x, see, and you're going to drop it into here. That's essentially what FTC does. Okay? So we get that this one is the cosine of x. Off topic, what's the antiderivative of cosine? Sine. Okay. Number 2, 1 over 1 plus t squared. What's the antiderivative of that? Because it is an antiderivative. Tangent. Tangent's derivative is secant squared. Inverse tangent. Inverse tangent's derivative is 1 over 1 plus u squared times the derivative of u. But in this case, it's just t, so you don't need it. All right. Has nothing to do with the problem. Just wanted to check that you remember your derivatives. So this guy gets placed right in there, and we end up with, I guess I can fit it there, 1 over 1 plus x squared. So much easier problems now. Takes a lot less time. The antiderivative of e to the t. E to the t. The antiderivative of e to the t is e to the t. Again, having nothing to do with the problem, because the problem, we're just going to do that. Notation does matter. Some of you think that putting this up there is the same as putting it down there, and it does matter. This is plus 2 after you do your e to the x. Alright, so then we get to 4, and then there's an issue. What's wrong with it? 3's at the top. How do I make it not be at the top? You take the negative?
No, you make it negative.
Why do I make it negative?
So that x can be on top.
So that the x can be on top. So I'm actually going to switch the upper and lower limits. That's the real rule that gives you that weird negative that you're talking about. So the rule is I can switch the integral limits if I give it a negative. That is another reason. I will take that reason. So, yes, it would be the same as f of 3 minus f of f, which would give you the negative of f of x. Perfect. Thank you, Ramsey. That works too. In this case, if you flip the limits, then this guy can come in, and you still get the negative of, and I'm going to actually just write the 1 with the negative. See, that's supposed to be an x. X plus 1. No. The antiderivative of that would be the ln of t plus 1. Of this, because if you take the derivative of that, it'll give you this. Because the derivative of the inside is still 1. Not perfectly absolute value. But, alright. Let's see. So, next page. Something's wrong. Now what's different? There's a function on top. Where did he come from? Alright, so here's what I want you to do. Only for the first one, we're going to try to figure out what the rule is. Because there is a quick rule, but you got to figure it out first. So you see that letter A? I want you to find the antiderivative, and I want you to do f of b minus f of a. Alright, so antiderivative was... Actually, I'm going to also give myself a little more space. Come on, come on. There we go. There we go. Alright, antiderivative was... We already discussed this one, I believe. Sine of t? We're good? Would it? The derivative of sine is? Therefore, no negative. You're thinking of the derivative of cosine, which is negative sine. Like I said, you're going to get confused. It happens. All right. So f of x squared would be sine of x squared. F of 1, you get sine of 1. Is there a variable inside of sine of 1? No. So if you could actually evaluate that, and just so you're very clear, no, you don't know the answer. It's not on the unit circle, by the way. Okay? So if you could find the sine of 1, you end up getting a constant number. And the answer is not 0. No, it is not. It is not. The sine of 1 would be 1 radian. 1 radian is about 57 degrees, I think. 52? 57? I think 57. I might be off. But, therefore, you don't know the sine of 57 degrees. Okay? So, that is some number. That's the key. The fact that it is a number. No, you don't need a calculator. Because then you're going to take the derivative of sine of x squared minus sine of 1. So let's do the sine of 1 first. What's the derivative of sine of 1? 0. That's why it didn't matter what it was. Okay? Now, I'm going to draw a little line there. Okay, next. Next, we're going to find the derivative of sine of x squared. So, derivative means we're going to use what rule? Chain rule. Derivative of the outside is cosine. Derivative of the... no, just kidding. What happens on the inside? Stays the same. Times the derivative of inside, which is 2x. So this is the answer to the original question. So let's figure out pattern. So what happened? Because it looks close. So what did I do with the x squared? I found the derivative of it. I added that. So that's there. And what did I do with this? Put it in for t. You just found the rule. That's essentially what you do. You take the function, put it in for t, and then you multiply by its derivative. So what I want you to notice, we've been doing that all along. You just didn't see it. I magically made it happen. What's the derivative of x? 1. So I took that whole thing and I multiplied by 1. Derivative of x? It's 1. So there was a 1 hiding back there in every single one of these. We just didn't talk about it yet. Okay? Because we didn't need to. Who needs to talk about it? Now we talk about it because this has a real, actual derivative, not just 1. So we'll do this the shortcut way. So we take this guy, we're going to place it. Oh, typo. I knew there was typo somewhere. These should be t's. And then these should be some letter. It actually doesn't matter what letter you pick. They just have to be the same. So typos, typos, typos. That's all my fault. Typo, typo, typo. Yep, things happen. All right. So letter B. Let's draw a little line here, and then we'll do that. Alright, so letter B. We're going to take this 3x and place it in for t here and t here. So we get 3 times 3x whole thing squared minus 4 times 3x plus 1, and the whole thing multiplied by 3. So I'll put it up front this time. You could potentially leave your answer pretty close to that. I probably would want at least the 3 factored. 3 squared is 9. 9 times 3 is 27. And then that's minus 12. And then plus 1. So that would probably be the most simplified. I'm leaving. Did I do something wrong? No? Okay. I leave the 3 factored out because I like factored versions. All right, letter C. Same thing. But something's wrong with C. We got to flip it. So I'm going to flip it and do the negative of 2 to 4x. Negify it. It is negated, maybe, would be a better word. Maybe. Who am I? I make up words all the time. All right. So, what do we get here? We're going to place that in for t. Place that, nowhere else. So just a big old negative multiplied by 5 times 4x, whole thing squared, plus 6, and then the whole thing multiplied by a 4. So my final answer would be negative 4 multiplied by 4 squared is 16 times 5 is 80, x squared plus 6. And then we get this ugly guy. Oh, that's not me. We get this last one, and something's royally wrong with that one. There's 2 x's, so something is wrong with that. Therefore, we're going to take that problem, and I'm going to add it in here. Insert. It was the integral, the derivative of the integral from x to 2x of, all right. So, most people don't figure this out on their own. I think it's hard to figure it out. You need a constant. Okay, that's the problem. You can't do this because there's no constant. So to make a constant magically appear, we're going to use a rule. There was a rule where you could find the integral from a to b plus the integral from b to c, and that gives me the integral from a to b. So that was that rule. Part plus part makes a whole. Area of a part makes a whole. Does that make sense? Okay. So now I got to make this a part and a part to make the whole. This is physically the whole piece. So I'm going to do the integral. So big old derivative. I'm going to do the integral from x to somewhere, and that somewhere doesn't actually matter. So you're going to pick a random constant. Yell out a number. 2. All right, 2 looks nice. No, you know what? Let's not use 2 just because that says 2x, and I don't want you to get confused in your notes. So 4 would be better, yeah. So I want you to make sure in your notes you say that that is some random constant. That is very random. Doesn't matter what it is. Lafika, please wake up. And then I'm going to put in my 5t squared plus 6 dt plus. So that's one part. I need another part. So where's my other part going to go from? From 4 until 2x. And then Anthony, I got you in 1 second. So then we're going to double check. Does that really work? Does it really work? So if I have a piece from x until 4, and then from 4 until 2x, is that the same as finding the integral from x to 2x? Doesn't matter. It won't ever matter. So let's do 4 to negative 3. You're just one step ahead of me. I just want to answer Laura's question. So the order of the values doesn't really matter because that's before 4. But that would be the same as me doing the integral from 4 until, let's even say, do you want this to be positive or negative? I don't know. All right, so that still works. Doesn't matter that that's before that. Doesn't matter that that's even before the constant that you picked. It still works. Okay? All right. Anthony, what's up? You can do it with, what did I say about the number 4? It can be what? It can be anything. I don't care what the constant is. Pick one. The reason why is going back to the original FTC1, did the constant ever matter? No. So if you want to pick e, go for it. You want to pick pi to the e, go for it. The square root of sine of pi, go for it. All of them will work because they're all constants. So then you just use the rules that you learned a second ago. This one, Danny, what was wrong with it? You're going to negate it, so I'm going to flip that guy from 4 to x of 5t squared plus 6 dt. And then this one is okay, but what I'm going to do, instead of doing this in 2 lines, I'm going to even say that when you find the derivative of terms, you can just do the derivative of the pieces. So I'm going to actually write the derivative over here also. That way it looks exactly like the problems we've been doing. Right? Looks good. So now, final answer in red at the bottom. So this would be negative 5x squared plus 6. This would be plus 5 times 2x, whole thing squared, plus 6 multiplied by 2. Simplify that guy and you get your answer. Okay? When you guys multiply 2x squared, that's 2x times 2x. That does become 4x squared. Sometimes you forget to square both parts of the multiplied term. All right. Any questions on this guy? That's pretty much all of it. So let's go through a summary of the things that you will forget and that will cause me to write exclamation part. Exclamation, 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 underline, underline, underline all over your test. So things that you have to remember. You have to remember, number 1, this only works if there's the derivative of an integral. If this piece right here is missing, then you can't use FTC1. So that's rule number 1. Rule number 2, your constant has to be where? on the bottom. The lower limit has to be the constant. The variable needs to be in the upper limit. And then the third major thing that you'll forget, what if the variable is a function? It's not just x, it's something like x squared. Then you got to multiply by the derivative. Okay, that chain is essentially the chain rule happening. That chain rule is really important. So this up here is actually considered the inside, because doesn't that go into the function? It goes in for the t. Therefore, that's the inside, so you're still multiplying by the derivative of the inside, just like normal chain rule. Okay? That's my little summary. You have one for your, not for your response, you have a multiple choice question that's ridiculously easy that I put at the end. Yeah, please don't get that wrong. All right. So, average time for a multiple choice question in the non-calculator part is 1 minute and 57 seconds. Okay? That's the amount of time you essentially get if we average it and say per question. What that means is this better take you like 4 seconds, and then you use the rest of the time on the harder questions where you would have to take the actual real antiderivative and substitute in numbers. That's how you gain your time. So things that are really easy, if you don't see that they're easy, that's how you end up running out of time. Because I do see people see this, and then they do the actual antiderivative, and they actually put in the f of b minus f of a, and then they take the derivative. Way longer. Okay? With that said, that's pretty much class. I can go over any questions that you have from last night's homework if you found something. I can give you the rest of the time to do your homework, which is like 7 minutes, but it's a nice 7 minutes, so I'm going to stop this guy.